Hello, I'm Laura Lewis, and welcome to Nuclear Equations and GCSE Physics. Okay, so learning objectives today. So an understanding of what is happening in the nucleus when an atom undergoes radioactive decay. Number two, equation practice for alpha decay and beta decay, and how this changes the mass and atomic number of an atom. And number three, explanations and further equation practice of decays involving gamma decay as a form of electromagnetic radiation. Okay, so first of all, to start off with, think about what alpha, beta, and gamma alpha particles, beta particles, and gamma rays are, and how are they different. So this is a bit of a revision. So what would be good to do would be to write down this table and to fill it in. You've done this in previous lessons because it would have come before nuclear equations. Whether it's my videos or someone else's. So it's good as it's a bit of a revision. Okay, so we have to make sure we know what this is first. Okay. Okay, I'll give you the answers now. I'll give you a chance to pause the video then. So let's have a look at an alpha particle. So an alpha particle is formed from 2 protons and 2 neutrons. Basically, it's a helium nucleus. So it's a helium atom without the electrons. Its mass is 4 mass units because it's got 2 protons and 2 neutrons, whereas a proton's got a mass unit of 1, a neutron's got a mass unit of 1. They've got the same mass. If there's 4 of them, it's got 4 mass units. It's as simple and straightforward as that. So what is its charge? So alpha is positive. Okay, so it's got 2 protons there and 2 neutrons. Neutrons don't have any charge, but protons have got a positive 1 charge each. So it's got 2 plus positive charge, so positive charge. Beta particle. So it's actually an electron, but it's an electron from the nucleus. It's not from the shells or the orbits, it's from the nucleus. So its mass, sometimes known as negligible, but it's about 1 over 2,000, that's a fraction, 1 over 2,000 of a mass, 1 over 2,000th, as a bit of a tongue twister, of a mass unit. Okay, so it's 1 2,000th of the mass of a proton or a neutron. It has a negative charge, like all electrons. Okay, and the last one, the more one that can catch people out, is a gamma ray. So it's an electromagnetic wave. It's not a particle. Okay, it has no mass because it's a wave. It has no charge. Okay, so neutral, no charge. So a quick look at some of the properties of nuclear radiation, just to remind ourselves. So it's a characteristics, and we look for 2 things in radioactivity. We've got penetrating power, so how easily it passes through the materials. We've also got ionizing power, so how easily it turns atoms into ions. Okay, so it's a good idea this is a good diagram to draw it down. Sometimes historically that these things are also all known as rays, so don't panic if you see that. Historically, if you get like a document, an old document, it might put a ray, but we know they're alpha particles. Okay, so highly ionizing, alpha particles, alpha, but it can't pass through paper. Moderately ionizing, beta. So beta can pass through paper, but not through skin, can't go into the body from outside. Gamma rays pass through paper, skin, and only be stopped by thick lead. Okay, so these are things to revise, because these things have been in previous lessons, just a recap to go over. Okay, so let's look at some questions that could be on that, because in an exam, what they'll do is they'll mix things up. So you could get a question about penetrating power of beta radiation, and the next one would be a nuclear equation about beta radiation. So they will mix these things up. Okay, so this is going to be a real exam. The alpha, beta, and gamma are types of ionizing radiation. State 2 ways in which gamma radiation is different from alpha radiation. So there's lots of different ways it's different. It's only 2 marks, so you only have to say 2 things, like it says. So you could say alpha radiation is a particle, gamma radiation is a wave or form of electromagnetic radiation. So you could say gamma radiation has no charge, but alpha radiation is a positive charge. You could say other things when you're about its penetrating power. You could say about ionizing, lots of things. You only have to have M2 there. And in the next one, complete the sentence by putting a cross in the box next to your answer. So a beta particle is emitted by, no, not an alpha particle, that's a different thing completely. Fusion, that doesn't make sense. process of elimination. A gamma ray, no. An unstable nucleus, yes. So it's emitted from the nucleus. Okay, I know that they'll ask that. That's why I always say I know they ask that a lot because it catches students out. And complete the sentence by putting a cross in the box next to your answer again. A beta particle has an identical charge to an electron. Negative. Okay. So you probably think in physics, why have we got a periodic table? Okay, it's a good question. The reason is when we do nuclear equations, we need to look at the masses and the atomic numbers of elements, and we need a periodic table to do that. So this is one, it's a very good one. See if we want to screenshot this, put the mouse over there. If we want to screenshot that, and print it out or copy it down, or in your book, and then maybe color code it. I don't mind. Okay, what you do, it helps you because it's a very good one. This one, it's used in the and a lot of exam boards at the beginning of the paper. It's one of the best one I could find. Okay. So yeah, you'll see later on why very important this is. So a larger number, usually at the top, but not always. So I would say the larger number. Okay, number of protons plus neutrons total is the mass number. So the bigger one at the top is a mass number. That's a chemical symbol. Okay, so I've got carbon C, oxygen's O. Okay, and it's got two letters like Cl for chlorine. Because they run out, because obviously C was taken by carbon, so chlorine has to have that Cl. Number of protons is the lower number, is the atomic number. Okay, so these are things again that they're, yeah, these are things that are important to know and to remember. Okay, so three isotopes. So looking at isotopes now, let's remind ourselves what an isotope is. We've got carbon 12, carbon. So when you say an isotope, you say the name of the element and then the mass. So carbon 12, then you say carbon 13 and carbon 14. Okay, so they've all got, if you look at them, they've got different mass numbers, but they've all got the same atomic number. Okay, so it gives you it here. So protons, 6, we've got 6, we've got 6 electrons. Neutrons for carbon 12, 6. Carbon 13, 7, carbon 14, 8. So they've all got different numbers of neutrons. So when you get atoms like this, which all have the same number of protons and different numbers of neutrons, then they're called isotopes. So they're isotopes of carbon. Okay, that's a key point there. So we've got two isotopes here, both chlorine, like I mentioned earlier, Cl for chlorine. So writing, so we've exercised writing the protons, the electrons, and the neutrons. Okay, so the answers. Okay, so they both got the same number of protons, same number of electrons, but they differ in the amount of neutrons they have. And you can tell that by taking this number from that number. Okay, so another example. Three answers. So we've got 3 isotopes of hydrogen. Hydrogen is the only element where it's got special names for its isotopes, but they can be generically known as hydrogen 1, hydrogen 2, hydrogen 3. Okay, so protium is the one that we know mostly. It's called protium, but usually just call it hydrogen. Deuterium, you may have heard of. It's got a neutron. Okay, it's got a friend. Okay, and tritium. Okay, it's got 2 neutrons and a proton, and they're isotopes. And then obviously you're at practice then of filling this out and then stating the similarities and differences between the isotopes of hydrogen. So this could be, it's a very common question. It could be asked with lots of different elements. Most elements have some isotopes. Carbon, we've just seen. Chlorine's got them. Carbon has got them as well. Hydrogen, many elements do. Okay, so there's the answers. So you should write down the correct one if you didn't get them correct. Right, so now we know all of that, we're prepared for our nuclear equations. Okay, so we've got balancing nuclear equations. So let's look at an alpha for a minute. Okay, so this is a nucleus of thorium, named after the Norse god Thor. Okay, lots of films recently. So this is thorium. If we don't know what that was, we could get, that's what I said about get our periodic table out and have a look. Okay, for thorium. So it's quite, what is its symbol again? Sorry, what's its number? So 90, so that's how we find it. Okay, 90. Let's go. Okay, so yeah, thorium. So if it's not on there, we'll be given it. Okay, we'll be given it here. So don't worry if you're not giving it at the front of your paper, you'll be given it on the exam paper. Okay, so we've got 90,228. That's its mass number, and that's its atomic number. So thorium decays by firing out an alpha particle to radium 224, and yeah, radium's got 88 as its atomic number, 224 is its mass, and an alpha particle. That's an example of an alpha decay. And obviously they have to, what we're saying here, all that you have to do is make sure both sides add up to the same thing. That's all you're really saying. So mass number 228, atomic number 90. Mass number of radium 224 plus 4, 228. Yes, that's the same as that. The overall mass is the same. Atomic number 90, atomic number 88 plus 2. This is the alpha particle. The alpha particle, because I said it is really a helium nucleus, it does have a mass and atomic number. That's 4, 2. It's got 4. It's got 2 protons and 2 neutrons. Added together to make 4. It's got 2 protons. Okay, so that's an alpha. Okay, that's simple enough, isn't it? Okay. So you go step by step through it here. Okay, so what I've been talking about, the difference. So you go step by step for alpha. So think about, this is another example of alpha. This is a very common one, radium to radon, because lots of rocks. Okay, so you might see this one as well, radium to radon. Radon's a gas, clearly known as. You can see 226 has gone down by 4. That's where it's gone into the alpha particle. 88 is going down to 6, so it's 2. Okay, so it all balances. Okay. The next thing we're going to look at is beta decay. So beta decay is slightly more complicated. Okay, so with beta decay, what happens is a neutron in the nucleus changes into a proton. Okay, so yes, it's a bit more hard to think about this one. So a neutron changes into a proton. So we've got potassium, okay. The symbol is K, potassium. Mass number 40, atomic number 19, goes to calcium. So this is where it's a little bit trickier. Calcium 40. So its overall mass number has not changed. Okay, but it looks like it gets an extra proton. But really, a neutron's changed into a proton. Okay, so it seems to get more, but overall, it's the same mass. And you've got a beta particle, -1, 0. Okay, so yeah, it's a little bit harder to get head around, I think, a beta decay. But again, it's the same thing. So it's basically the same, mass is conserved. It's a bit like in chemistry, so mass is conserved. The same thing happens here. Also charge, yeah, so charges can be conserved, but another video I'll talk about that. So mass number 40, atomic number 19. So mass number 40 plus 0 goes to 40. Atomic number 20, and then -1 is 19. Yeah, that's what it's a bit harder to think about. I think that's why. But it's just an electron from the nucleus, and as long as we understand that a neutron is changing into a proton, I think you'll be okay there. Okay, so yeah, so it goes through, okay, of how we did that. Okay, it goes through it. So I'm going to do some examples a bit later. Okay, so sort of a checkpoint here. Okay, to still like to check an understanding of the alpha decay process. So sort of checkpoint here, and here is the answer. Okay. Beta decay again. There is a checkpoint here. That's to check if you understood to yourself, sort of a self-assessment really. See if you understood. Okay. Okay, now we'll look at some practice. Okay, so I'm going to just so I can write in it. Right, nuclear decay. Well, so we're looking at some practice now. So equation practice. So polonium, let's have number 2 next to it, it doesn't really matter. Okay, let's put that in. Just auto formatted itself. So polonium 204, that's how we say that, decays by alpha emission. So 204 polonium, yep, named after the country of Poland. It's Marie Curie's home country. It's named after her home country. So polonium 204, 84. So gone down to Pb is lead or plumbus in Latin. So 204, 200. So it's gone down by 4. 84 to 82, gone down by 2. And this is an alpha particle. So if you ask an exam to fill in, the mass of an alpha particle is 4. And the atomic number is 2. It's as easy as that. Okay. So this one got radon 224 decays by alpha emission. So we've got 2 alphas here. 224 radium 86. So the alpha we know it's got a 4. We didn't look at our periodic table, we've given it. So 224. So 224 minus minus 4 to 20. Okay. Remember, it doesn't have to be the same as that one. It could be an isotope of polonium. Okay, so don't panic if it's different. Polonium has different isotopes. 86 down to 84, but it will have the same atomic number as that polonium. It's the same element. It'll have the same atomic number. Okay. And the next one, a little bit, not really that difficult, really. So strontium 90 decays by beta emission. So 90, 38. Gamma, sometimes, sorry. Strontium 90 is going to beta emission, not gamma. 90 strontium 38 goes to yttrium. Okay, so I'll double check what that element is. You don't need to, it's just out of interest. Okay. Yeah, in an exam we won't be asked exactly what that element is because yeah, it's yttrium. Yeah, I supposed to be correct. Yttrium, named after a village in Switzerland. Yttrium. Okay, let's just wanted to double check that. I wouldn't tell you the wrong thing. Yeah, it's yttrium. Okay, so strontium 90 decays into it goes by beta emission. Now beta, remember 0, the number, and minus 1. Okay. So this is phosphorus. Okay, piece of phosphorus goes into sulfur. So 3215. Phosphorus goes into 3216 sulfur, and beta, remember 0 and minus 1. Okay, so if we didn't know, I'm going to just get rid of that. We'll get rid of the symbol. Okay, so if we were given that without the sulfur, okay, we'd be told to find that. So pretty much this, you can see that the mass number hasn't changed. Top number doesn't really tell us what it is because different isotopes can be different. So because phosphorus, so 16. So we can look for 16. Now, we weren't told what it was. Okay, we could get that in an exam, which just got the element missing like that, and we're given a periodic table. Okay, we look for 16, sulfur, S. Okay, so yeah, beta decay could be they could ask for missing things. They could ask you the whole thing. Okay, so capital S for sulfur. Okay, so that's a beta decay. So remember this stays the same. So the number of neutrons plus protons stays the same. That's the atomic number goes up as the neutrons change into a proton, so it goes up. Okay, the last, but it's kind of like it catches people up, but it's the easiest one, really. The gamma decay. Okay, gamma decay, it also looks like nothing's happened. Okay. Okay, this because you might not have seen the other video. But obviously I'll talk about it now anyway. It's a gamma decay, you've got uranium 235, okay, goes to 92, or 92 atomic number. This is symbol for gamma. It's a Greek letter gamma. 0, 0, no charge, no mass. Stays the same. Okay, so if you get a gamma decay in an exam, you don't really have to do anything because no, it's gamma. If nothing's changed, it's gamma. Okay, well, nothing appears to have changed anyway, I'll say that. Okay, so yeah, because they're energy. They're not particles, they're just energy. So yeah, it has no impact on the actual mass or anything, or the charge of nucleus. What the nucleus does is actually rearrange itself. So if you want to know a bit more, is that it's a way of the nucleus losing energy to rearrange itself. Okay, so I hope that's been good. Okay, so a bit of a practice of all those things, and Thank you for watching and goodbye.